In this series, we are going to explore the fundamental data structures in computer science. In this video, we are going to talk about linked lists. The linked list data structure is a collection of nodes, where each node stores a piece of data and a reference to another node. The nodes are linked in a list structure through their references. As this is a rather general definition, we can identify different types of linked lists. One of the simplest useful forms of a linked list is the singly linked list. It contains nodes that include a reference only to the next item. The last node in the list usually has a no reference, which is used to identify the end of the structure. If we develop the nodes of the singly linked list further, so that they contain a reference to the previous node in addition to the next node, we now have developed what is called a doubly linked list. If the last node of the list does not contain a no reference, but a reference to the first node, the structure becomes circular. This type of list is called circly. Linked lists have inherent advantages and disadvantages when it comes to running time performance. Search is not an efficient operation with lists. The algorithm must go through each item sequentially. At the beginning of the list, mutations are efficient as the linked list contains a reference to the first item. In the middle, mutations of the structure take constant time, but you need a reference to the node you want to mutate, or the previous node in a singly linked list. Because of that, a mutation in the middle of the list takes search time plus constant time. Note that practically, a vector or array will outperform a linked list at mutations in the middle. Vectors use contiguous memory, which means they can utilize memory cache more efficiently. The complexity of mutations to the last item in the list depends on the design. A linked list can include a tail, which is a reference to the last item. If a tail is implemented, the operations at the end are efficient, taking constant time. A tail reference can be implemented for both singly and doubly linked lists, and is required to implement a circular design efficiently. Now let's explore some use cases. A great use case for a doubly linked list is the previous and next functionality in a web browser. The data contained in the nodes in this case is the page URL. When the user clicks one of the buttons, the previous or next references in the node are used to retrieve the URL in constant time. Linked lists can also be used to implement other data structures like stacks and queues, which we'll talk about later in the series. Before we implement a linked list, I'm first going to design the API using UML diagrams. The main building block of the list structure will be the node class. As you see in the UML class diagram, we're using a template class, so that the implementation will be capable to store any abstract data type in the nodes. If you're not familiar with UML class diagrams, this diagram item represents a single class. At the top, we list the class name. Beneath that, we list the class attributes, and lastly, we list all of the methods. The plus and minus signs in front of attributes and methods show if the item is public or private. Minus means private, and of course, plus means public. The node class has two attributes, data and next. Data will store the actual node data, while next will be a pointer to the next node in the list. The methods are symbol getters and setters. They'll be used to retrieve and mutate these two properties. The other class we'll use for the implementation will be the linked list class. It has only one attribute, the head, which stores a pointer to the first node of the linked list. Now let's go through the methods. Push will insert a new node at the beginning of the list as the new head reference. Append will insert a node at the end of the list. Insert after will insert a node after another node. Insert at will insert a new node at a specific index. Pop will remove the first node. Remove tail will remove the last node. Remove node will remove a specific node from the list. Remove at will remove a node at a specific index. Lastly, at will retrieve a node from a specific index. To implement the doubly linked list, we will have to modify the node class to include a previous reference, together with, of course, the necessary getters and setters for it. The circly linked list can be implemented as both doubly and singly, and the API design does not change if the list is circly, only the implementation details. Now, finally, let's jump to the implementation. We'll start with an empty C++ project in Visual Studio and a single main.cpp file. I like to first write a simple main function to test if my project setup and development environment work correctly. This main function will just output text to the console. As you can see, everything is working as expected, and we can move on with the linked list implementation. I will implement a singly linked list. I'm first going to create a folder, which I'll call singly, and I'll use it for organizational purposes only. Now let's create the node class. I'll create a new header, which I'll call node. I will encapsulate the linked list in a new namespace. I'll call it singly. The class will be a template, so that the data structure can hold any abstract data type. Now, following the UML diagram, we'll first define the private attributes. First will be the data, which will have the template type. Second, the next node reference, for which I'll use a smart shared pointer. I do have to include memory in order to use a shared pointer. The next thing we have to do is define our public methods. I should mention that I'm doing this with the UML diagram open to the side, which makes the implementation much easier. I'll first define a 0-parameter constructor, a 1-parameter constructor with a single data attribute, and a 2-parameter constructor with data and next attributes. Next, we'll implement the getters and setters, starting with data. The getData method with tReturn type, and the void setData method with a parameter of type t. We have to do the same for the next attribute. The getNext method will return a shared pointer to another node, and the setNext void method will accept a single parameter, which will also be a shared pointer to a node. Now we have the class definition, and we can go forward with the implementation. I would usually put the implementation in a separate .cpp file, but as this is a template class, I can't do that easily. So I will do the implementation in the header file beneath the definition. We start with the 0-parameter constructor. It will set data to null and next to a null pointer. The 1-parameter constructor will accept a single parameter. I'll call it input data, and it has type t. We'll use that to set the data to it, and we'll once again set the next attribute to be null pointer. The 2-parameter constructor will have both attributes as input parameters, and we just have to assign them. We'll follow the definition order and implement the getData method. It is only a getter that returns the data attribute. The setData method will be void and have a single parameter of type t. We'll call it input data. We just set data to the input parameter. Next is the setNext, which is void, with a single input next parameter. We again set the next attribute to that input parameter. The getNext method will return a shared pointer to a node, and its implementation will just return the next attribute. With that, our singly node is fully implemented. We will now create the linked list class. In order to do that, we'll create a new header file for it, which I'll call linked list. Everything has to be in the singly namespace. The linked list class has only one private attribute, and that is the head pointer to the first node. It will be a shared pointer to an instance of the node class. I need to include memory again, and also the node.h file. We'll start the public properties with the constructor. This implementation will include only a 0 parameter constructor. Next is the push void method. It accepts a single parameter of type t, which will be the data. The insert after method is also void and accepts two parameters. The first will be a pointer to the node after which to insert, and the second will be the data. The append method is void and accepts a single data parameter of type t. The add method will return a pointer to a node and accept a single unsigned integer parameter, which will be an index. The pop method will be void and does not require any parameters, as it will always remove the head node. Next is remove tail, which will remove the last item. Remove node will also be void, and it will accept a pointer to the node, which we want to remove. Remove at will accept a single parameter, which will be the index, so we need an unsigned integer type. Finally, there is the getHeadGetter, which will return a shared pointer to the head node. Now, we'll start implementing the methods one by one. The constructor will only set head to a no pointer. The push method has to insert a new item as the head. We'll create a new node with the provided data. We'll use the two-parameter node constructor and pass input data as the first argument and the current linked list as the second argument. As the head is pointing to the current head, this node is now connected to the linked list. The only thing left to do is to set the head reference to the new node. Insert after accepts a node pointer as the first parameter, which I'll call refNode, short for reference node, and data as the second. We will create a new node again using the two-parameter constructor. This time, the next reference in the new node will be the next reference of the reference node, which we get using its getNext method. We do that in order to insert the item between the two existing nodes. Lastly, we set the next reference of the reference node to new node. Quite simple and efficient, as you can see. The append method accepts a single data parameter, which I'll call input data. We'll again create a new node. This time, we'll use the one parameter constructor to only set the data. Now, we have to find the last element in the list. In order to do that, we will create a temporary pointer, which I'll call temp. We'll set it to the head node and write a while loop. The while loop will run until the next item of temp is not a new pointer. Until that is true, we'll set temp to the next item. This way, we'll go through the linked list until we reach the last item. The last thing we need to do is to set the next reference of the last item which is now temp, to the newly created node. The add method will return a pointer to a node and accept an index as its parameter of type unsigned int. Similar to append, we'll create a temporary pointer to the head. This time, we'll use the for loop and run it until we reach the input index value. We'll store the next reference in a new variable and check if it is a null pointer. In case it is, we'll return the current value. We will also set temp to next. I did make a mistake here, but we'll talk about this later. Next is the pop method, which is void. We first have to check if head is a null pointer, in which case we do nothing. Otherwise, we set head to the next item in the list. The remove tail method will need the node, which is before the last node. So we store a temporary pointer to the head. And while the next item to the next item is not null, we iterate and set temp to the next item. Now, this is error prone, and we need to do an extra check here. I also forgot my template type in the definition. We need to check if the next item is a null pointer first. And in that case, we actually need to just set head to null pointer, as that is the only item in the list. And we need to stop the function here, so we return. Finally, at the end, we need to set next of the temp item to null pointer. The remove node implementation has a reference node parameter. I will first need to check if the node is the actual head. In that case, we use the pop method and return. In all other cases, we store a temp pointer to the head, and again, we iterate until next equals node. When we find the right node, we set its next pointer to the next pointer of the input node. This will actually remove the input node. Remove at accepts a single unsigned int parameter, which is an index. You probably know the drill by now. We create a temp pointer and use a for loop to reach the index. This time, we'll search for index -1, as we need the previous node. We check if temp is a null pointer and stop the function in that case, as the index is basically invalid. Otherwise, temp has to be set to the next item. We need to do one additional check after the loop if the next item is null. And if all that is correct, we remove the next item, like this. The final method we need to implement is just the head getter. It will return a node pointer, and will just return head. Now let's go to our main function to test the linked list class. I must include memory and the node and linked list header files. I'll first create a new linked list to store integers. I'll call it list1. Let's add a few data nodes to it. I'll use push. Let's do 1, 2, and 3. I'll also append a 0 test insert after, I'll add an item after the second node. I'll add 2 and change the push numbers so that they will be output in correct order if everything is working correctly. Next, I need to iterate through the list to output all data nodes in order. To do that, I'll store a pointer to the head, and I'll iterate through each item and output its data on a new line. On each iteration, we also have to increment the pointer to the next node. Let's also output the item at index 3. We'll do that using the add and get data methods. I run this now and I did get an error. If you remember, I told you before that I did make a mistake at the add method. It should always return at the end of the subroutine. After we fix that, we can run the program again. And as you can see, the implementation is working as expected. Today, you learned what linked lists are, how they perform, and how to implement them. They're not great at everything, but because of the great insertion and deletion performance, they are an excellent solution to some use cases. Stay tuned for the next video when we will use a linked list to implement another data structure, a stack.